Okay, so I've got the formula for flux up here. I want to just say one thing about notation. I've already mentioned that I'm not crazy about the book's choice to call the surface S, because I think it's easy to get confused. That's the name of the surface, that's surface area, okay? The book makes another choice that I like even less. They sometimes will write this as the double integral over S of f dotted with ds, writing this as a vector. Now, what that means is n ds. That's the unit normal vector scaled so that its magnitude corresponds to a small amount of surface area. I don't like that. I just don't, okay? Because that suggests that surface area is a vector. And I'm sorry, area is not a vector quantity. It doesn't have direction. This makes clear. The direction is the direction of the normal, and then that's a small amount of surface area. That tells me what it means. That doesn't, okay? So I did need to point out that that's how the problems are going to be written in the textbook, and you can use that notation. It is considered accepted notation. I think it's misleading and a very, very poor choice, and I'm just not willing to use it, so I'm not going to. I'm always going to write dotted with n ds. Okay, that's the direction, and then that's a small amount of surface area. But that's what's meant by that vector ds in your textbook. Okay, so I want to practice evaluating a flux integral. So I'm going to let S be the top half of the sphere of radius 2, centered at the origin, oriented out. Okay. And by out, I mean away from the center of the sphere. Now, obviously, we're just talking about the top half of the sphere here. So I could just as well have said oriented upward, because we will also have an upward component if we're going away from the center of the sphere. Okay, but we're going to be working just with that top half of the sphere, where the whole sphere would be centered at the origin. Okay, I'm going to let F just be, let's go with Z, Z, Z. Okay, so that's going to be my vector field. I'm going to calculate the flux of F across S. Okay, now I'm just giving you a vector field and we're calculating this. This could be the result of scaling a velocity field by the density function, in which case the flux would represent the mass per unit of time. Okay, I want to just get a couple of flux integrals under our belt, and then we'll return to the notion of what does flux actually mean if the vector field that I'm working with isn't a velocity field or a velocity field scaled by the density function. Okay, but let's just practice working with this. Okay, so if my surface is the top half of the sphere, I'm going to need to come up with a formula, a parametrization of that, and I'm going to go ahead and parameterize that in terms of theta and phi. Now, since it is just the top half of the sphere, I know that the sphere would be x squared plus y squared plus z squared equals 2 squared, which would be 4. So the top half of it would be z equaling the positive square root of 4 minus x squared minus y squared. But this square root is going to be 0 on the circle of radius 2 where the sphere intersects the xy plane, because my z value is 0 there. And my partial derivatives would put this exact same radical in the denominator, so I would get an improper integral if I tried to use that parametrization. So with a sphere, I'm going to almost always parameterize in terms of spherical coordinates. Okay. So remember, on a regular basis, x is rho sine phi cosine theta. Rho is now held constant at 2. So x becomes 2 sine phi cosine theta. Y would be rho sine phi sine theta, so that becomes 2 sine phi sine theta. And z is rho cosine phi, so that becomes 2 cosine, cosine phi. Okay. All right, if we're getting just the top part of the sphere, looks like theta is still going to be going between 0 and 2 pi, but I'm going to restrict phi to be just between 0 and pi over 2. Because when phi is pi over 2, that puts me on the xy plane. If I rotated past that, I'd be below it, and I only wanted the top half of this sphere. Okay, so I've come up with a parametrization. Now, I don't know, I'm actually lying because I do, I don't know whether this orientation is outward or inward, okay? I just know that's my go-to parametrization for a sphere, okay? So, let's keep up our vector field. I'm going to have to check. When I take the cross product of the partials, I'm going to have to figure out whether that gives me the right orientation or not. So let's find our partials. Del r del theta would be, let's see, 2 sine phi, oh, negative. So negative 2 sine phi sine theta. Then I'll get 2 sine phi cosine theta. And then I'll get 0, because there are no thetas in my z component. Del r del phi is going to be 2 cosine phi cosine theta, 2 sine phi, I'm sorry, 2 cosine phi again, sine theta, and then negative 2 sine phi. Okay, so del r del theta crossed with del r del phi. That's what I'm going to refer to as a non-normalized normal vector. It's not going to be my principal unit normal vector. To get that, I'd have to normalize it. But when I'm calculating a flux integral, I don't bother to, because the magnitude of this vector is the scaling factor that I get when I switch from integrating ds to integrating dA. So let's see, I think I'm just going to remember this information so that I can clear some board space. So this is going to be symbolic determinant I, j, k, negative 2 sine phi sine theta, 2 sine phi cosine theta, 0, 2 cosine phi cosine theta, 2 cosine phi sine theta, negative 2 sine phi, which is going to give me a vector. Okay, so for the i's, I'm going to get negative 4 sine squared phi cosine theta. For the j's, I'm going to get negative 4 sine squared phi sine theta. And for the k's, I'm going to get negative 4 sine phi cosine phi times sine squared theta minus 4 sine phi cosine phi cosine squared theta. Now, in this third component here, I can factor out a negative 4 sine phi cosine phi, and that's being multiplied by sine squared theta plus cosine squared theta, and of course that's just 1. So my third component is just negative 4 sine phi cosine phi. So that makes it a little bit simpler. Okay. Now, this is going to be normal to the surface. I want to know if it's normal and points outward, because we were told we wanted to work with this oriented outward. Okay. So, I'm going to have to figure that out. Okay. Well, if I'm working with the top half of the sphere, okay, I want to just pick a convenient point there to see what that normal vector should be. I want to make sure that I avoid the very topmost point, because if you'll remember, when we parametrize the sphere using spherical coordinates, it's technically not smooth at the very top point and at the very bottom point. And that's an ignorable problem, but that means when I'm checking my orientation, the very top point and the very bottom point are not good places to choose to check. I think what I'm going to do is I'm going to check the frontmost point. Okay. So on the frontmost point, that would be the point where I intersect the positive x-axis. If at that point we're oriented outward away from the center of the sphere, the normal vector would be pointing straight forward. The x component of the normal vector would be positive. The y and z components would be 0. But if I have a positive x component, that's pointing away from the center of the sphere. Okay. So I'm going to check that point. And that point would occur when theta is equal to 0, because I'm on the positive x-axis, and phi is equal to pi over 2. So I'm just going to evaluate this at that particular point. So del r del theta crossed with del r del phi evaluated at the point 0 pi over 2 is going to give me, let's see, sine of pi over 2 is 1. Okay, so sine squared is still going to be 1. Cosine of 0 is 1. So both of these factors are 1, so I'm just getting a negative 4. Now, that's really all I need to see. That's pointing back towards the center of the sphere. I'm going to just show that I do in fact get 0, 0 here, just to confirm that this worked. Okay, notice theta is 0, so sine of theta is going to be 0, and phi is pi over 2, cosine of phi is going to be 0. So that's actually pointing in the wrong direction. I wanted to be pointing outward. So I went to a parametrization that I knew and loved. It gave me the wrong orientation. So that's the normal vector that points in the right direction. I'm going to just introduce a negative sign, which is going to change the sign of each component. Okay. So that's what I mean by checking to see whether the orientation works or not. When you have a parametrization, generally speaking, I'm not going to say, you know what, I'm only going to use this parametrization if it gives me the right orientation, because very often I have a parametrization that I know, but I'm not familiar with what the orientation is. So I just calculate the orientation that comes with that, and if it gives me the wrong one, I take its opposite. So that's exactly what we've done right here. Now, I could, obviously I'd get the opposite vector if I just took this cross product in the opposite order. So one way of getting this would be to think of it, instead of theta as my first parameter and phi as my second, if I make phi my first parameter and theta my second parameter, so that I'd be crossing these in the opposite order, that would also give me the correct thing. But I want to make sure that this is the vector that I get for my non-normalized normal vector. Okay, we've been going for a little while, so I'm going to stop this video and we'll finish up this problem in the next one.